Okay, welcome everybody. This is the week 9 webinar. We're getting close. And hopefully everyone's doing well. Let me tell you the plan today. As always, I'll answer any questions that you have throughout the time, but also at the beginning and the end, whatever. Always happy to answer questions. And then you'll notice all the rest is all about chi-square. Okay. So we're going to be kind of looking at the chi-square distribution, which is we've had a lot of different distributions already, and this is a new one. So we've had the uniform distribution, the normal distribution, the binomial distribution, the t-distribution. So we've had a bunch, and now we're going to be looking at the chi-square distribution, which is used for many purposes that are things that we have not been able to handle yet with the others. Okay, and we'll talk about that. Specifically, if we have qualitative data with not just a yes/no question, but with maybe 5 answers or 100 answers, um, we don't know how to do that yet. We have not covered that yet in class, and that's what chi-squared is going to help us with. Okay. Then we're going to look at the chi-squared goodness of fit test. So that's one of the tests that use the chi-square distribution, and it's called goodness of fit. Then we'll look at the chi-squared test for independence. Again, are things independent or not? And we'll be able to use the chi-squared test for that. And then finally, the chi-squared test for homogeneity. And we'll see how that is. So we're going to have 3 different chi-square tests this time. And just to let you know, this is chi-squared. The chi kind of looks like an X, but it's not. It's a Greek letter, and it's pronounced chi, and then it's squared. So that's just a note. Just a reminder, this is an odd week. It's week 9, so there's no exam. But what that means, one thing it means is that you should have a little extra time. So I strongly recommend getting started on your project 2, so that, this is a week that's a little lighter than others. So use that time for doing your projects. And again, you should have partners. And if you haven't already, please, please post your idea on the Project 2 discussion board. Make sure you state what your null hypothesis is, what your alternative hypothesis is, who your client is, how you're going to collect your data, which does not necessarily have to be a survey. It could be a data on just collecting data from whatever set of data you can find, as long as you can't collect the whole population. But sometimes, using the internet or wherever it might be, you can collect data that way too. This is not like Project 1. Okay. But please post your idea on the Project 2 discussion board, and I can let you know whether it works and possibly some improvements that could be made to make it even better. And that way you won't fall into a trap and not have a good project that doesn't work. So that's really important, is to post it. Okay, and I do check the discussion board often, so please post. Okay, so that is the plan today. It's not that hard a day, which is the good news. Um, but who knows? Some people have more trouble. You know how it is. So let me ask you, are there any questions about anything? Okay, I don't see any questions in the chat box. I do want to give you a heads up that I'm going to tell you specific words that have to be used when you're answering written questions, whether that be for the discussion board assignments or whether that is for the exam, which will be in week 10. But if you don't use the words I tell you have to use, then I take a lot of points off. One of the reasons I do that is that way people actually pay attention in the class, actually have to learn instead of just use AI to do everything. Because AI will not use necessarily the exact words I tell you. So that's just a big note. And hopefully everyone is paying attention. So there aren't any questions. Let's take a look at the chi-square distribution. It's going to be a kind of picture. And if I go to the calculator, and if I go to interactive statistics, which is behind the calculator away, and you will see visualize the chi-square distribution. And this is what the chi-square distribution looks like. You'll notice it's not a distribution that we have really spent a lot of time with yet. It is skewed right. Is that clear? Because there's a big peak far to the left, and then it kind of slowly goes down on the right. It's skewed right. It's unimodal. It has one peak. And one thing about the chi-square distribution that the other distributions do not have is a property that there are no negative values for the chi-square distribution. Okay, and that you might expect because of the name chi-squared. If you square something, you don't get a negative number. Right? If you square -4, you get positive 16. So the chi-square distribution is always positive, so there's not gonna be a left-tailed test for this week. There won't be two-tailed tests, there's only right-tailed. You only have, positive values, so you don't even look at the left side, you look at the right-hand side. And there's also something called degrees of freedom. If you have 5 degrees of freedom, it looks like this. If we lower it, then you can see that the graph changes and it becomes very skewed right. And pretty soon it just goes up, 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 up on the left. If you make the degrees of freedom much bigger, it actually gets looking more normal. It's not perfectly normal, but it looks pretty normal at 18 degrees of freedom already. Or if we go all the way up to 20, which is what I have in my code, then it's not exactly normal. It's slightly skewed right, but not much. Okay. And we'll talk about these degrees of freedom in a little bit and kind of see where that all comes from. Any questions on kind of the picture of this distribution? Okay, let's go back and now let's do some examples. Today's an example day. I want to let you know that the chi-square distribution is used a lot in research. So published papers. It's not used in day-to-day stuff, but it is used a lot in the published paper stuff when you're doing research. So just let you know, all the examples I give you are just going to be kind of, I just made up a bunch of numbers, but when you go and look at articles, which you're going to have to do for the discussion post assignment, then you'll see chi-squared is not hard to find. So here comes an example. Okay. And that is in California, 40% of residents are Latino. 34% are white. You may not know that, but California has more Latinos than whites. 16% are Asian or Pacific Islander, and 10% are other races. That might be African American, it might be Native American, or whatever race you might be that isn't either Latino, white, or Asian Pacific Islander. Okay. So one of the questions you might ask is, if you look at California community college students, does it match the distribution of races for all of California? Because the idea is one of the things we hope to do is we hope that we represent California. We don't want to be biased in any, direction, only say we only want this race. We want to make sure that we really have a good, a good diversity at which we are kind of reflecting or mirroring what California looks like, since we're California community colleges. Okay. And then I should probably say, suppose a survey was done, because I did make this up. A survey was done of 300 California community college students, and 125 were Latino, 92 were white, 33 were Asian or Pacific Islanders, and 50 were other races. What can be concluded at the 5% level of significance? Okay. So you'll notice the survey question here is, what is your race? And it's not a yes or no question. It's not a question where you just give a number. I'm 73. You wouldn't say that for your race. You wouldn't say yes. Okay. You would say, hey, I'm white or I'm a Latino or you know what I mean? You would give one of those words. So this is qualitative. It's a qualitative survey question. It's not yes or no. We have not dealt with that at all in this class. Have you noticed that in terms of hypothesis testing? Okay, we've defined it, but we haven't worked on that. So we don't know what to do yet. So what we want to do is we are going to write down a null and alternative hypothesis. Okay, so here is H naught. H naught is a null hypothesis, and it's the following. The distribution of races at California community colleges is the same as the distribution of races in California. Okay, hopefully you know by now. Why did I highlight this word distribution and scream it out? How come? At this point, you should know. We're late in the class. We've been lots of weeks in the class already. I've done this lots of times. I don't see you popping in your chat box, but hopefully you remember. Yeah, it's a key word, and more importantly, if you do not use it when you have to write down the null hypothesis, then I take off a lot of points. Okay? It has to, if you do not have the word distribution when you're doing this kind of hypothesis test in your H naught, then you lose points. Got it? Okay, so the distribution of races at California community colleges is the same as the distribution of races in California. Okay, H1 is the distribution of races in California community colleges is not the same as the distribution of races in California. One nice thing, especially with online classes, everything's at the computer. So once you have typed out your H naught, you literally can just copy, paste it, and put in the word not. So it's really easy when it comes to typing for H1. Okay. Any questions on this so far? Okay, I do want to give you a heads up, and that is you'll notice this is very different than H naught and H1 for what we did in the last couple chapters, because H naught and H1 are all words. Okay? And that's different than what we had in chapter 9 and 10, where I told you had to have symbols. Okay? And that's because it really doesn't work. It really does not work with symbols when it comes to this chi-squared stuff. So just let you know that H naught and H1 will be in words, not in symbols. And that'll be a requirement. Whereas anything from chapter 9 and 10, those must be in symbols. Any questions on H naught and H1? All right, so the next step we have to do is create a table. Okay. Actually, maybe the next step would be decide on the test to use. And that is going to be called a goodness of fit test. And a goodness of fit test is used when you have one known distribution where you know the distribution of an entire population and you have a different population that you don't know the distribution of. And you have a sample for the other population, this different distribution, or this different population. You have a sample for that. And you want to find out if the distribution from the population from what you don't know is the same as the population that you do know. Anyone lost on what I just said? Because a lot of words there. And that's one of the hard parts about this week is knowing which test to use. Okay, so this is called the goodness of fit test. Because the idea is, hey, does it look like it fits? Do community college students fit the distribution of all of California? That's why they call it goodness of fit. So the next step is we need to write out a table. So in the table, our columns will be the races. Latino will be that first column. White will be the second. Asian Pacific Islanders the third. And the other will be the fourth because those were the answers to the qualitative question that was asked. Okay. This is the letter O, by the way. It's not the number 0. And O stands for the word observed. Okay. So the next thing you do is you write down how many were observed. Okay. Well, how many Latinos were observed? 125. Because that's what it says. 125 were Latino. So I put 125 right here. Okay. The next were 92 were white. So I put 92 here for the whites. The next were 33 were Asian Pacific Islanders. So under the Asian Pacific Islanders, for the observed, I put 33. And the next were 50 other races. Those were observed. So 50 under the other observed. Any questions on that part of the table first? That's usually pretty easy. You just have to read it. You have to remember to do it. Any guess on what E stands for? The first letter of something important. Close, but just one word. Expected. Yeah, so it's the expected. Okay, so E stands for the expected. And the idea, if we surveyed, which, in this question, they surveyed 300 California community college students. How many would you expect, okay, if it really is the same as all of California, how many would you expect would be Latino? How do you calculate that or come up with that? How would you figure out how many you would expect to be Latino on a survey of 300 California community college students given this information here? Any ideas? I don't see you jumping in, but it might take a while to type. It's not that long. It's just a number. Yeah, you take 40% of 300 because, again, if it's the same as all of California, you would expect 40% to be Latino. Now, 40% of 300, 4 times 3 is 12, by the way. And then because it's a percent, you drop a 0, and it's 120. So you would expect 120 to be Latino. Okay. And to find out how many you expect to be white, that would be 34% of 300. 34% of 300 is 102. So you take 0.34 times 1 times 300, and you get 102. You're welcome to use a calculator. You don't have to do it in your head like I did, but that's up to you. Okay. And 16% are Asian Pacific Islander. 16% of 300 is 48. And then 10% are other races. So 10% of 300, that's easy. That's 30. Any questions about creating this table? Okay, so now that we have this table created, we could look at this and say, hey, did we get what we expected? Is 120? Is that what we expected? 120. Did we get 120 Latinos in our survey? What do you think? I don't see y'all jumping in. Okay, we didn't get 120, we got 125. So you might say, hey, we didn't get what we expected, so hey, it must be different. But this is statistics. And you got to look at that. There's random chances. So it's not that did you get exactly what you expect, but did you get so far away from what you expected that that would be too unlikely. So you say that no, based on our sample, we have statistically significant evidence that the distribution is different. Or maybe it's not that far away. 125 doesn't look that far away from 120. So then you say, hey, we don't have statistically significant evidence to show that you have different distributions. Okay. You could also look at 92 versus 102, 33 versus 48, 50 versus 30. They're all different, but are they different enough? And what the chi-squared test does is it does a calculation to find the probability that if the population of all California community college, in terms of the racial population of all California community college students, was the same as California, what would be the probability of getting these differences that we got? Okay. So that's kind of what that is. And that probability, or at least getting at least that different, that's the p-value. Okay. Which we've done for a couple weeks now. P-value is very important. What do you think the next step is? What's the next step? And by the way, this is about racial distribution. Almost certainly going to use a 5% level of significance because anytime you have sociology, that's 5% is what people use. So what's the next step? Yeah, we go to the calculator. So let's go to the calculator. What calculator do I use? This should be really obvious. I tried to make it obvious when I made this calculator. I did not try to hide anything. What number? 22. This is a goodness of fit test. Okay. And what it says is type in the values from the observed and expected set separated by commas. Okay. Hit calculate, and then we'll get everything we want. So observes are 125.92. $33.50. And the expecteds, 120, 102. And then 48 and 30. And I hit calculate. And it gives me everything I need. Okay, this chi-squared, that's the test statistic. In this case, it's about 19.2 or so. Okay, and then, by the way, the p-value is about 0.000247. Okay, it's tiny. Here's the picture of the chi-square distribution. Notice it's very skewed right. Okay. It turns out there's 3 degrees of freedom. It's one number of degrees of freedom is one less than the number of choices that were in the survey question for goodness of fit. So it's 4 minus 1, which is 3. And that's what the picture looks like. And we're way over here for our test statistic, 19 something. And that's way, way in the rejection region area. So again, here's the test statistic, here's the p-value, and I'm ready to state the conclusion. So here, notice the p-value is less than 0.01, in fact. So that means we can use the word strong. And it starts, you should be used to this first part. There is strong, statistically significant evidence to conclude that. Okay? Those are the words that have to be there. Okay? And then the idea, what's nice about this is I can just copy H1 and then paste it right here and make the lowercase. The distribution of races at California community colleges is not the same as the distribution of races in California. And that's our conclusion. Any questions on that? Okay, I just want to let you know something that you can't do from chi-squared. You can say the distribution is different. Here's what you can't conclude. You can't talk about why it's different. You can't say, hey, which group is the one that's really different? All you can say is the distribution is different. When you do a chi-square test, that's all you can say. Okay? You cannot say, that means that there were, you know, more Latinas than the in community colleges, California community colleges, than in the state in terms of percent. You can't do that. All you can say is that you have different distributions. And that's really important to know. Any questions at all? Any questions at all on this? Okay, very important. And hopefully you see that this is used. Okay, it's used anytime you have a survey where you want to compare a population that you know to a population that you don't know, and it's qualitative data. Ready for another example? Okay, so here's another one. Does it matter what season a person was born when it comes to the type of car they drive? Okay. The table below shows the season and car type. Okay. And what we have is spring, summer, winter, and fall. And we have sedan, SUV, and other. Okay. For example, anyone want to guess? This year, what kind of car have I driven the most? Any guess? My guess is none of you are going to guess. But you never know. No one wants to say? Okay. All right. You can say SUV. I'm as other as it gets. This is going to sound really weird. I haven't driven this year. I hate driving. I have a car, but I haven't driven it. So I walk, I ski, I bike. But, eventually I have to drive because I have to leave the mountain. So I'm another. But then we have spring, summer, winter, and fall. And I would be a summer person. I was born in July. And for me, it's other because I haven't driven anything. Okay. So this 51, just to let you know what these numbers mean, that means of the survey that was done, 51 of the people were born in the summer and drive another kind of car. Whereas, say, 76 of the people were born in the winter and drive a sedan. So that's how you read this table. Okay, these are a table of counts in the table. Any questions on reading the table? Okay. And what we want to do is we want to say, hey, it doesn't matter what season they were born. It's kind of similar to astrology. And some people believe in it, but I'm all about statistics. I look at statistics and see if it makes a difference. Okay. And you can do this with chi-square distribution. Any questions so far? Okay, so the next thing, can we use goodness of fit for this? What do you think? That was our last example. We talked about goodness of fit. Can we use goodness of fit? You think so? Okay, I don't see all of you answer. The answer is no. Okay, goodness of fit is when you know a distribution of a population. Then you have another population that you don't know its distribution. You take a sample and you compare it. That's not what this is. We don't know any distribution here. We're not comparing two populations. We're not doing that. What we're looking at is we're looking at two survey questions. One survey question is, what season were you born in? The other survey question is, what kind of car do you drive? Do you see that? And we want to find out if knowing what season a person was born in is going to help you guess in a, better way what kind of car the person drives. Does it make any difference? Okay. We had a word for that. I know this has been a long time ago. This was week 2, and we're already week 9. In week 2, we had a word for that. Do you remember the word? To find out if knowledge of one survey question helps you determine chance for the other survey question to have a certain answer. Do you remember? Again, it was a long time ago. It was in January and pretty early January. Okay, I don't see y'all jumping in. That was independence. We wanted to find out if season born and car driven are independent or not. Okay. In early January, we just looked at one of these numbers, but now we're going to look at the whole thing at once. And we're looking for independence. So it turns out the name of the test we're going to use is the chi-squared test for independence. And that's used when we have two survey questions. They're both qualitative, and we want to see if they are independent or not. Any questions on that? And that's called the chi-squared test for independence. Very important. So here are H naught and H1. So H naught, the null hypothesis, is the season a person was born in and the person's car type are independent. You heard me scream it. So that means you better put it if you're asked to write down the null hypothesis for a chi-square test for independence. If you don't have the word independent there, you lose points. Okay. And H1 is the season a person was born in and the person's car type are dependent. So the word dependent has to be in H1. Got it? Okay, so again, you have to, first know what kind of test to use, and then you better use the right language. Take notes, whatever it takes, so that you know what to put in. Any questions at all on H naught and H1? Okay, what do you think the next step is? Notice we already have a table that's given to us. What's the next step? Yeah, we go to the calculator. And this is not goodness of fit, so I better leave it. And what test do you think we need to use? What number? Yeah, this is a test for independence. This is 23. And here we go. So this says enter in the observed values and hit calculate. Okay, and the chi-square test and the p-value will be calculated for you. Chi-square test statistic and the p-value be calculated for you. Leave blank the last rows and columns that don't have data values. Okay. And I just want to let you know in this calculator, it only allows for these columns to have at most 5. If you need to have more, you need to use a spreadsheet. And you can use the one for our project actually if you wanted, but I will let you know that's never going to happen for anything you have to do for our class. Could happen in reality someday for you, but not in our class. So then it tells us what to put in. So now we're going to go and we'll put numbers in. 73, 81, 76, 78, 65, 68, 62, 64, 43, 51, 48, sorry, yeah, 48, 50. Okay, and that's all. So we just scroll down and hit calculate. And there we go. Here's our test statistic and our p-value. Okay, we have our chi-squared. Okay. And by the way, the degrees of freedom now, you notice now we have two survey questions. It's actually going to be, there's 3 minus 1 is 2, 4 minus 1 is 3. That's going to be 6, but degrees of freedom. But you don't have to know that with this calculator, but it lets you know there are degrees of freedom. And here's the chi-squared is about 0.48 or so. The p-value is 0.998. Okay. I wanted to be made this somewhat realistic. If a p-value is 0.998, what does that tell you? Yeah, it's failed to reject, and there's no chance. You wouldn't even think about doing another study. Does that make sense? With a bigger sample size. Because there's it's so close to one. At that point, you give up and you say, I'm not even, think they're dependent. Okay. And I tried to make it realistic because at least I feel that it has nothing to do with when you were born and what kind of car you drive. So trying to make that realistic. So, so here's our chi-squared, here's our p-value, and we can state the conclusion. There is statistically insignificant evidence to make a conclusion that the season a person was born in and the person's car type are dependent. Okay, so notice you can just literally copy and paste the season a person was born in and the person's car type are dependent. That goes right here. And what came before that was what you're used to when you have a high p-value. There is statistically insignificant evidence to make a conclusion that. Do you see how this is coming, like really coming right from what we had done before last week and the week before? It's the same beginning, and the end is just H1. And if you have a big p-value, you have insignificant evidence. If you have a low p-value, you have significant evidence. Any questions at all on this kind of test? The test for chi-squared test for independence. Any questions? Okay, should we continue on? All right, let's do another example. So, do single men and women take the same type of vacation? The table below shows the results of a study. And again, I made these numbers up, but you can imagine a study being done. And we looked at international, out of state versus more local. and then male and female. Okay. And here's what we got: 29, 47, 33, 38, 42, 36. Okay. So is this a test for independence? What do you think? I don't see y'all jumping in. The answer is no. Because that, if it was a test for independence, then it would say that. Then it would say, is gender and travel type independent? Does that make sense? What this is we're looking at men and we're looking at their distribution of travel type. We're looking at women and we're looking at their distribution of travel type, and we want to see if they're the same. So is this goodness of fit? What do you think? Yes or no? Because we're comparing two different distributions. Is it goodness of fit? Yes or no? Okay. Why is it not goodness of fit? We have two distributions. Goodness of fit has two distributions too. For example, the example we did, we had the California Community College racial distribution, and we had the California racial distribution. Those were two different distributions also. So that's not the reason. I don't see you jumping in. So let me tell you, the big difference between this one and the first example is that here we don't know the population distribution for either of the populations. We don't know the population distribution for men, and we don't know the population distribution for women. We don't know either. We only have samples for both of them. Whereas for goodness of fit, you know the population of one, and you want to see if it's if something that you don't know is the same as what you know. Here we don't know either. Any questions on that? So we use what's called, it's a different kind of test. It's called a chi-squared test for homogeneity. Do you know what the word homogeneity means? You might have heard the word homogenized, like homogenized milk. Do you know what the word homogeneity means? I don't see you jumping in. Homogeneity, like homogenized milk, because it's kind of mixed in together. It means everything is like all together and they're the same. So that's why they call it a chi-squared test for homogeneity. Okay. And by the way, I am going to ask you, what is the name of the test that you need to use for the written questions, by the way. So you do have to state the name of the test. Okay. So H naught is the distributions of vacation type are the same for men and women. Notice what's different about this one from goodness fit is it's plural. This is the distributions that we're comparing are the same. So that one's got an S at the end. And again, it's the distributions of vacation type are the same for men and women. You got to have that word in there. Distributions. And H1 is the distributions of vacation type are not the same for men and women. You heard me scream it out. Okay, that means you better put it on your exam if you're using homogeneity. Okay, and on your discussion post assignment if you do have homogeneity. Any questions at all on H naught and H1? And I do want to let you know everything has been H naught and H1 for all three types of tests here that we do today. are sentences, not symbols. It's all words. Okay, what's the next step? Yeah, we go to the calculator. And this is not a test for independence, so I'm not going to use this one. Let's go back to the calculator menu. And what test number are we going to use? Yeah, 24. Okay, which might make you smile a bit because look how close we are to the end of the course. There's only two left. And just let you know, there's 2 weeks left of this class. So there's going to be next week we'll do regression analysis, the week after we do ANOVA. So this week we have 3 different ones, but they're not that hard. So I'm going to use test for homogeneity. And here it says enter the observed values for each of the 2 samples, A and B, and click calculate. And the chi-squared test statistic and p-value will be calculated for you. Leave blank the last rows that don't have data values. So now we had 29, 47, 33. So 29, 47, 33. That's our A. And then B, 38, 42, 36. So 38, 42, 36. And hit calculate. And there we have it. Okay. By the way, this has a very small, this has a very small degrees of freedom. And that's why this one is, doesn't even look close to being normal. Okay. So, and the reason in this case we just had an A and a B, and there were just 3 types. So it's just 2 degrees of freedom. And it gave us our chi-squared was about 1.91, and our p-value was about 0.384 or so. I do want to give you a heads up because when I graded your discussion post assignment, at least one of you had a p-value greater than 1, and you should worry. P-value can never be bigger than 1. Often you just got to look way over to the right and see an E something, and that tells you scientific notation. So I want to give you that heads up so you don't make that mistake again. Okay. So we have our chi-squared, we have our p-value. And p-value is pretty large here. Okay. Notice we didn't even look at the level of significance. You don't with chi-squared. You just use the right wording. So if you have something that is 0.49, you never have statistically significant evidence. Whereas if it was say 0.07, then you would say you have weak statistically significant evidence. If it was say 0.03, you would say you have statistically significant evidence. And if it was 0.002, then you would say you have strong statistically significant evidence. So typically in the real world, people use those special words to talk about how good the evidence is. So here, there is statistically insignificant evidence to conclude that the distributions of vacation type are not the same for men and women. Any questions on this? Any questions? Make sense? Okay. Um, just let you know, this is I'm not going to do a full example, but I actually use this stuff a little after I turned 21. What was I allowed to do after I turned 21? Yeah, I gambled. I was a card counter. Yeah, I didn't drink much alcohol, but I was a serious card counter because I'm a statistician. And what they would do is they would come in and they would cheat. They'd bring in a cheater. And what I would do is I would do a chi-square test to see whether the distribution of cards for the dealer was the same as the expected distribution of cards for the dealer. Okay, and if it wasn't, then I would know that they were cheating, and I would leave the table. Then I'd come back like another hour from then, and then it'd be a different dealer, and then I'd be fine. But in those days, some of the dealers cheated. You know, they were working for the casinos, and they made money that way. But that's something I did, and it was kind of the way I can like make that cheating not happen. I can't gamble anymore. Do you know why? I can't go into the casinos and gamble. Yeah, they told me that they would kill me if I ever came back, and that was in Vegas. And I would just talk to someone. Again, I use statistics. It's all about statistics. And I talked to someone who's act does that at the casino. That's their job to identify card counters. And she said my name is on their list. I'd never even been to the casinos in Tahoe and gambled, but I'm on a list. So you can make money on this stuff, but be careful because they will kick you out forever or worse. Okay, so that, and I used chi-squared to be able to decide whether the distribution was the same. Okay, kind of fun stuff. Okay, shall we do one more example? Today's kind of a lighter day. I told you it's a lighter week. We're not going to have to go a whole hour and a half. Okay. So here's an example. A study was done asking 100 people how many minutes they spent in the shower last time they took a shower. The mean was found to be 16 minutes and the standard deviation was 4 minutes. Okay, the table shows the results. Is the distribution normal? This is very different than anything we've looked at before. What what do you think the right test would be to find out if the distribution was normal? This is actually really important because if you remember, when we looked at the central limit theorem, that you could not use a normal distribution for the sampling distribution if you had too small a sample size and you didn't know the distribution is normal. So a lot of times you test to see if the distribution is normal if you don't have a big sample size. So what test do you think we're going to use to decide whether the distribution is normal? Yeah, now it's goodness of fit because what we're doing is we have the distribution of shower time that we don't know the distribution, and we want to compare it to the normal distribution. We do know what the normal distribution is, you know, the bell curve. We know exactly what it looks like. Okay, so this is going to be a goodness of fit test. Okay, so here's what we're going to do. Here's what was observed. There were 20 people who spent less than 12 minutes in the shower last time they took a shower. There were 73 that spent between 12 and 20 minutes last time they took a shower. And there were 7 that spent more than 20 minutes last time they took a shower. Any questions on that? That's the given data from this survey that you can imagine having been done. Okay, since it's good as a fit, we do observed and we do expected. Now we got to figure out how we figure out the expected. How do you come up with the expected value? Right? The expected number that was, say, between 12 and 20. Let's do this middle one first. Turns out it's the easiest to start with. Any idea on how we can do that? How we find the expected? don't see y'all jumping in. Okay. It's been a while. It's been about 3 weeks or so. Okay, and that is we use the empirical rule. Notice that 16 minutes was the mean, 4 minutes was the standard deviation. So if we do 16 minus 4, we get 12. If we do 16 plus 4, we get 20. So the x between 12 and 20 is the same thing as you're within 1 standard deviation of the mean. What percentage of the data is between 1 standard deviation of the mean for a normal distribution? Who remembers? This is the empirical rule. Been a few weeks. Do you remember? The percentage of the data within 1 standard deviation of the mean is what percent? I don't see you jumping in. All right, let me remind you in case you forgot. 68%. Do you remember that? That was the empirical rule. 68% of the normal distribution is within 1 standard deviation of the mean. Now here's a really easy question. What's 68% of 100? I tried to make the numbers nice. You should all be able to do that without a calculator. 68% of 100 is? Yeah, 68. Okay, now we need to find out the expected values less than 12 and greater than 20. Well, the normal distribution is symmetric. Okay, so that tells you that the number here, less than 12, needs to be the same as the number here, greater than 20. Well, there's 68 in this middle area that came from the 100 people. So if there's a 68 in the middle area, there's 100 minus 68 outside the middle area. 100 minus 68 happens to be 32. So if there's 32 total outside, how much are on the left? 16, because 32 divided by 2 is 16. How much are on the right? That should be really easy. 16 again. It's symmetric. And now we have our observed and we have our expected. Any questions on that? Okay, we're using a goodness of fit test. So we write H naught. The distribution of shower time is normal, because that's what we're showing. We're trying to show it isn't. That's H1. The distribution of shower time is not normal. Any questions on that? What's the next step? Yeah, we go to our calculator. So let's go back to the calculator menu. And we already decided it was good as a fit test. And it says observed and expected. The observed were 20, 73, and 7. So 20, comma, 7, 3, comma, 7. The expected were 16, 68, and 16. And I hit calculate. And there we go. We have our chi-squared. Our test statistic is about 6.43. Our p-value is about 0.04. Okay. And again, if we think about this, this is shower time. 0.05 is probably about the right thing to do, but we're just going to use the right wording. So here's what we can write. So here's our chi-squared, our test statistic, our p-value. And here's the conclusion. There is statistically, so we have our p-value was 0.04. So now we have statistically significant evidence, not strong, because 0.04 is not less than 0.01. So in this case, we just say there is statistically significant evidence to conclude that. And then you just look at the H1. The distribution of shower time is not normal. So that the distribution of shower time is not normal. And that's the conclusion. Any questions at all on how this test works? Just let you know, there's kind of three main uses of goodness of fit. One is when, again, you know, like the population of California, you know, because you can find that online. And then there's one that you don't know when you're comparing it. Okay. Another is to see if the distribution is normal. Okay. And it turns out there's a more sophisticated test, but we're not doing that in this class because this is elementary statistics. So just let you know that if you do take more stats classes, say in upper division statistics, then you're going to hear about some others. Okay. Then there's one other type, which I'm not going to show you an example of, but it's not hard. Besides normal, what is the next most commonly used distribution? Do you remember? Which we had a half a chapter on in our class that you're testing to see if it is. So sometimes you want to find if it's normal, because if it's normal, then you can, use the calculator. But what's the other one we know how to do and do calculations easy that we want to test to see if it is? And also you want to test because it's interesting. Remember? There's one other distribution type. Yeah, uniform. So sometimes you want to find out if the distribution is uniform. Okay. And one reason is if it's uniform, then hey, everyone's treated the same, no matter what their grouping is. Whereas if it's not uniform, that means some are treated differently. Do you see that? Or some have different personalities or whatever it might be. So sometimes you'll see uniform. And just let you know, uniform is very easy. If for the distribution for the expected, if you have a uniform distribution, and let's say there are 5 groups, then each group, the expected would be 20% for each, because 20% times 5 is 100%. So to find the expected for a uniform, you would just take 20% of the sample size, and every single one of the expected numbers would be that number. So uniform means the expecteds are all going to be the same number that have to add up to the sample size. Any questions on that idea? Okay. As I mentioned, this is not too hard a chapter because you should be working on your project a lot this week. But the secret word is distributions. So distributions. Distributions is the secret word for the week 9 webinar, for this week's webinar. Okay. So make sure you write down the words distributions, because if you remember, for homogeneity, that was a word you had to put in to count it for full credit if you're asked for H naught and H1. And the conclusion too is distributions. Okay, so that's the secret word for this week. And what I want to remind you again is spend time in working on your project this week. Very important. Okay, because don't wait till the last minute. That's never good if you wait till the last minute. If for some reason you don't have a partner, get yourself a partner. Go to the Project 2 discussion board and post. See what other people post and see if you can add to them. If there's 2 people in a group, see if you can be number 3. Okay, so it's very important that you can make sure that you have a partner, and hopefully by the end of this week, you also have your project idea. Okay, any questions? Okay. What I'm going to do, I think we're done for the recorded webinar. So I am going to stop the recording as always. Next week will be, now it's every other week. Every week is the opposite. So this week was Tuesday. Next week will be Monday. The week after will be Tuesday. And then that's it. So just let you know in terms of our webinar dates. Okay, so I'm going to stop the recording. Thanks for coming. And